Long before the first dinosaur ever took a breath, our planet was a realm almost unrecognizable to us today, a world shaped by forces and life forms that have long since vanished. Picture the Earth over 300 million years ago, during the Carboniferous period, when the continents were unrecognizable, and the very air was thick with the breath of ancient forests. Instead of barren deserts or windswept plains, the land was dominated by immense humid swamps. These were not mere marshes, but sprawling primeval jungles shrouded in perpetual mist and alive with the sounds of countless unseen creatures. The forests themselves were unlike anything that exists today. Towering club mosses, some exceeding 30 meters in height, formed dense canopies alongside gigantic horsetails and ancient ferns. Their bark was thick and scaly, their leaves arranged in spirals, all competing fiercely for the precious sunlight that filtered through the heavy, moisture-laden air. The atmosphere was saturated with oxygen, reaching concentrations up to 35%, nearly double what we breathe today. This oxygen-rich air was a product of the relentless photosynthesis carried out by the vast forests, and it gave the world a dense, almost tangible quality. In this supercharged environment, life responded in extraordinary ways. Arthropods, freed from the constraints of modern oxygen levels, grew to monstrous proportions. Millipedes like Arthropleura stretched over 2 meters long, while dragonflies, such as Meganeura, soared through the canopy with wingspans rivaling those of modern hawks. The continents themselves were slowly merging, forming the supercontinent Pangaea. This vast landmass was still in its infancy, but its assembly was already reshaping global climates and ocean currents, setting the stage for dramatic evolutionary changes. Across this immense continent, the climate was overwhelmingly tropical. Warmth and moisture prevailed, creating a greenhouse world where lush vegetation blanketed the land from pole to pole, and seasonal changes were subtle, if present at all. The endless wetlands provided a haven for early vertebrates. Amphibians, some as large as crocodiles, thrived in the shallow waters, while the first true reptiles, small, agile, and covered in tough, scaly skin, began to explore the drier fringes, testing the boundaries of terrestrial life. Beneath the dense canopy, the forest floor was a thick, spongy mat of decaying plant material. Over millions of years, this organic debris was compressed and transformed, forming the vast coal beds that would one day fuel the engines of human industry. Invertebrates reigned supreme. Giant millipedes, scuttling scorpions, and armored eurypterids prowled the undergrowth, while swarms of insects filled every ecological niche from the leaf litter to the highest branches. The atmosphere was thick with unfamiliar sounds, the rustle of enormous wings, the clicking of armored legs, and the distant croaks of amphibians echoing through the fog. The sights were equally alien, strange silhouettes moving in the gloom, bizarre forms adapted to a world of perpetual dampness. Above the canopy, the air vibrated with the deep, resonant hum of Meganeura's wings. These dragonflies, with their massive compound eyes and needle-like jaws, were apex aerial predators, hunting other insects in a deadly ballet. On the shadowy forest floor, evolution was experimenting with form and function. Some creatures developed armored plates for protection, while others evolved elongated bodies to slip through tangled roots and decaying logs. Early tetrapods, the ancestors of all land-dwelling vertebrates, crept cautiously through the labyrinth of roots and fallen branches. Their limbs, still splayed to the sides, allowed them to push through the mud in search of prey, while always remaining close to the water's edge for safety. The ecosystem was in perpetual motion. Plants grew at astonishing rates, only to be consumed or toppled by storms. Predators hunted relentlessly, while scavengers and decomposers broke down the remains, recycling nutrients back into the soil in a never-ending cycle of life and death. But this lush world was not eternal. As the Carboniferous period waned, subtle shifts began to reshape the landscape. The once endless swamps started to recede, replaced by stretches of drier, more open terrain. The assembly of Pangaea altered global weather patterns. Vast interiors of the supercontinent became increasingly arid, with pronounced wet and dry seasons, challenging the dominance of swamp-adapted life. Swamps that had stretched for thousands of miles began to shrink, their margins invaded by drought-tolerant plants and the first true forests of seed-bearing trees. The creatures that had flourished in the wet, oxygen-rich world now faced a crisis. Many could not adapt to the drier, more variable climate, and their numbers dwindled as new challenges emerged. As the Carboniferous gave way to the Permian, the world was transformed. New landscapes appeared, and with them, new opportunities for evolution. The stage was set for the rise of entirely new groups of animals, better suited to the changing world. The reign of the giant insects was ending. In their place, more adaptable vertebrates, ancestors of the great reptiles and mammals, were poised to inherit the Earth, ready to dominate the next chapter in the planet's unfolding story. After the lush, swampy forests of the Carboniferous faded into memory, the Permian period emerged nearly 299 million years ago, unveiling a world transformed by relentless geological and climatic forces. The Earth was no longer a patchwork of continents and shallow seas, but a single immense landmass, Pangaea, spanning from the frozen southern pole to the humid tropics and up to the northern reaches. Pangaea's formation dramatically altered global climate patterns. With so much land clustered together, the interior regions became isolated from the moderating influence of the oceans, resulting in a climate of unparalleled extremes. The heart of Pangaea was a vast inhospitable desert, where rainfall was scarce and the sun's intensity was unrelenting. Here, the land baked under a merciless sky, and temperatures soared to levels that would be lethal for most modern life. Along the coasts, conditions were somewhat more forgiving, with seasonal rains and milder temperatures, but these regions were narrow ribbons compared to the immense arid interior. In this unforgiving environment, survival demanded extraordinary adaptations. Every day, ancient creatures faced a relentless struggle against dehydration, searing heat, and the constant threat of starvation. The skies above were often shrouded in a haze of volcanic ash, the result of frequent and violent eruptions that punctuated the Permian landscape. These eruptions not only darkened the sun, but also released vast quantities of gases, altering the atmosphere and further challenging life below. The land itself was a mosaic of barren rock, shifting dunes, and scattered patches of hardy vegetation. Rivers, once abundant, dwindled to seasonal trickles, and lakes evaporated under the relentless sun, leaving behind salt flats and mineral crusts. In the heart of summer, ground temperatures could exceed 60 degrees Celsius, creating a lethal environment for any organism not perfectly adapted to such extremes. Compounding these challenges, the atmosphere itself was changing. Oxygen levels, which had peaked during the Carboniferous, began to decline, making the air thinner and every breath more taxing for the animals that roamed these ancient lands. Yet, even in the face of such adversity, life found a way not only to persist but to flourish. In isolated pockets where water and nutrients were available, ecosystems teemed with a remarkable diversity of plants and animals, each uniquely suited to the harsh realities of the Permian world. The dominant vegetation of this era was unlike the sprawling, moisture-loving forests of the past. Instead, the land was dotted with plants that could withstand drought and poor soils. Conifers, cycads, and ginkgos, with their tough, waxy leaves and deep anchoring roots, spread across the drier uplands, forming resilient woodlands that could survive months of searing drought and sudden, violent storms. These hardy plants became the foundation of a new food web, supporting a complex array of herbivores and predators, each adapted to exploit every available resource in this challenging environment. Among the most remarkable inhabitants of the Permian were the synapsids, a lineage of animals that would eventually give rise to mammals. Unlike the reptiles that had previously dominated, Synapsids possessed a unique skull structure and a suite of physiological innovations that set them apart. Many, such as the therapsids, began to develop characteristics we now associate with mammals, including more efficient metabolisms and the first signs of warm-bloodedness, a crucial advantage in a world of temperature extremes. This internal heat regulation allowed them to remain active during the cool dawn and dusk, as well as to withstand the punishing midday heat, giving them access to food and territory unavailable to less adaptable species. Over time, synapsids diversified into a spectacular array of forms, from nimble insectivores to massive armor-plated herbivores and formidable apex predators, each occupying a distinct ecological niche. The Permian truly belonged to these pioneering creatures, who ruled the land with unmatched tenacity and innovation. The landscape itself was a dramatic patchwork of volcanic mountain ranges, parched plains, and the last remnants of ancient river systems, each shaped by the relentless forces of plate tectonics and erosion. Frequent geological upheavals meant the ground was often unstable, riven by fissures that belched sulfuric gases and clouds of ash, further complicating the struggle for survival. Against this ever-changing backdrop of fire, dust, and drought, the great monsters of the Permian carved out their existence. Towering predators stalked the open plains, pursuing heavily armored herbivores in a relentless contest of strength, speed, and endurance. Competition was fierce, not only between predator and prey, but among species vying for scarce resources and against the very environment itself, which offered no mercy. Every day in the Permian was a crucible of adaptation, a relentless test of evolutionary ingenuity, where only the most resilient and resourceful could hope to survive and thrive in a world of extremes. To truly grasp the origins of the Permian's remarkable creatures, we must journey further back in time, to the lush primeval world of the Carboniferous period. This was an era unlike any other, a time when the very air itself was transformed by the relentless growth of vast forests. Towering lycopsids, horsetails, and ferns formed dense, shadowy canopies, their fallen trunks and leaves accumulating in thick, spongy layers that would one day become coal. The atmosphere was saturated with oxygen. Levels soared to over 30%, far higher than today, creating a world where life could take on extraordinary forms. In this oxygen-rich environment, invertebrates flourished as never before. Their simple respiratory systems, composed of branching tubes called tracheae, allowed them to absorb the abundant oxygen directly from the air. This physiological advantage enabled them to reach sizes that defy modern imagination. The undergrowth teemed with creatures that, by today's standards, would seem monstrous, yet here they were the norm. Dominating the skies was Meganeura, a griffin fly whose delicate veined wings spanned nearly 70 centimeters. Unlike any modern insect, Meganeura soared above the swampy landscape, its multifaceted eyes scanning for prey. With a body built for speed and precision, it hunted with relentless efficiency, snatching up smaller insects in mid-air. The constant hum of its wings was a signature sound of the Carboniferous, a reminder of the aerial supremacy these ancient predators enjoyed. Beneath the tangled roots and decaying foliage, another titan made its slow, deliberate way. Arthropleura, the largest land-dwelling invertebrate ever known, stretched up to 2.6 meters in length. Its elongated, segmented body was shielded by overlapping plates, providing formidable protection as it moved through the damp, shadowy undergrowth. Despite its imposing size, Arthropleura was a gentle giant, subsisting on rotting plant material. Its powerful jaws ground down the fibrous remains of ancient trees, recycling nutrients back into the ecosystem. Fossilized trackways reveal the immense weight and deliberate pace of this creature, a silent architect of the Carboniferous forest floor. Yet, not all inhabitants of this world were so benign. Pulmonoscorpius, a colossal scorpion, prowled the leaf-littered ground. Reaching lengths of up to 70 centimeters, It was armed with robust pincers and a venomous stinger, perfectly adapted for ambush. Pulmonoscorpius hunted with patience and precision, preying on the early amphibians and primitive reptiles that ventured too close. Its armored exoskeleton and predatory instincts made it a formidable force, a reminder that danger lurked in every shadow of the Carboniferous swamps. The reign of these invertebrate giants was a direct consequence of their unique world. The oxygen-rich air, the dense forests, and the absence of large vertebrate competitors allowed them to thrive and diversify. But this golden age was fragile. As the Carboniferous drew to a close, the climate shifted. Swamps dried, forests receded, and oxygen levels gradually fell. The very conditions that had enabled such extraordinary growth began to vanish. One by one, the great invertebrates dwindled, unable to adapt to the changing world. In their place, new forms of life began to rise, vertebrates with lungs and sturdy limbs, ready to seize the opportunities of the Permian. The age of giant insects and arthropods faded, but their legacy would echo in the bones and behaviors of the creatures that followed. As the Permian world continued to evolve, the balance of power shifted dramatically. In this ancient, unforgiving landscape, a new lineage of predators began to assert dominance, forever altering the course of terrestrial life. These were the therapsids, an extraordinary group of synapsids whose emergence marked a pivotal evolutionary transition. Unlike their reptilian predecessors, therapsids displayed a suite of advanced features that set them apart as the apex hunters of their time. Many therapsids were developing endothermy, or warm-bloodedness, a trait that allowed them to maintain high levels of activity regardless of the fluctuating Permian climate. This adaptation granted them superior stamina and agility, enabling them to traverse vast, arid plains and dense forests in pursuit of prey. Among these formidable hunters, one genus stood out for its sheer predatory prowess, Inostrancevia. This apex gorgonopside was a master of stealth and power, stalking the Permian wilds with calculated precision. Inostrancevia reached lengths of up to 3 meters, its elongated skull a marvel of evolutionary engineering. The robust jaws and reinforced cranial structure were perfectly adapted for dispatching large prey with lethal efficiency. Its most iconic weapons were its enormous saber-like canine teeth, which could extend up to 15 centimeters. These formidable fangs were not designed for crushing bone, but for slicing through flesh and delivering devastating, deep wounds. With a single well-placed bite, Inostrancevia could sever arteries or pierce vital organs, ensuring a swift and fatal end for its victims. Its hunting style was a blend of patience, power, and surgical precision. Yet Inostrancevia was not alone in its reign. The Permian plains teemed with a diversity of predatory therapsids, each adapted to exploit different ecological niches. Among these, the Dinocephalians produced their own behemoth, Archosaurus. This colossal predator was a testament to the evolutionary arms race unfolding in the Permian. Archosaurus was one of the earliest true giants among terrestrial predators, reaching lengths of up to 6 meters and tipping the scales at nearly a ton. Its sheer size alone would have made it a dominant force in its ecosystem. Despite its name, which means early reptile, Archosaurus was a highly advanced synapsid, boasting anatomical innovations that foreshadowed later mammalian predators. Its most distinctive feature was a massively thickened skull, reinforced to withstand tremendous impacts. Paleontologists believe Archosaurus used its head as a battering ram, either to stun prey with bone-shattering blows or to engage in brutal combat with rivals for territory and mates. Despite its bulk, the structure of Archosaurus's limbs and spines suggests it was surprisingly agile. This predator could launch sudden, powerful charges, pursuing even the largest herbivores with relentless determination. The gorgonopsid family, to which Inostrancevia belonged, displayed remarkable diversity in hunting strategies. Some specialized in ambush, while others relied on endurance and speed to run down their prey. Inostrancevia was the consummate precision killer, but its close relative, Rubigea, embodied a different approach, one of overwhelming force and aggression. Rubigea, similar in size to Inostrancevia, was even more robustly built. Its skull was broader and reinforced, designed to withstand the stresses of powerful bites and violent struggles. This predator possessed one of the most formidable bites of the Permian, capable of crushing bone and rending the armored hides of even the most well-defended herbivores. Its jaws were engines of destruction, evolved for brute force predation. Rubigea was less a silent assassin and more a relentless brawler, using its immense strength and ferocity to overpower any creature that stood in its way. Its confrontational style made it a terror of the ancient world. In many ways, Rubigea represented the zenith of gorgonopsid evolution, a culmination of millions of years of predatory refinement, standing at the apex just before the end of an era. But not all therapsid predators were giants. The Permian world was also home to a host of smaller, highly specialized hunters that filled vital roles within the ecosystem. These nimble carnivores relied on stealth, speed, and intelligence, often employing ambush tactics or coordinated group strategies to secure their meals. One such predator was Lycaenops, whose name means wolf face. This slender, agile gorgonopsid was roughly the size of a modern large dog, with a streamlined body built for pursuit. Fossil evidence suggests Lycaenops may have hunted in packs, using teamwork to bring down prey much larger than itself. This social behavior would have given it a significant advantage in the competitive Permian environment. With proportionally large eyes, Lycaenops was likely adapted for hunting in low-light conditions, such as dawn, dusk, or even during the night. This allowed it to exploit times when larger predators were less active, reducing competition and increasing its chances of success. The Permian landscape was thus a tapestry of predatory innovation, from the bone-crushing might of Rubigea to the swift, coordinated pursuits of Lycaenops. Each species carved out its own niche, contributing to a complex and dynamic ecosystem. These Therapsid Kings, in all their diversity and specialization, stood as the ultimate rulers of their world. They were the last and greatest of their kind, reigning supreme until the cataclysmic events at the end of the Permian would sweep them away, paving the way for new forms of life to rise. In the relentless arms race of the Permian, every formidable predator was met with an equally formidable defense. The herbivores of this era were not passive victims but living fortresses shaped by millions of years of evolutionary pressure. Their bodies became battlegrounds, where natural selection sculpted armor, bulk, and bizarre weaponry to counter the ever-present threat of predation. Among these armored titans, Scutosaurus stood as a paragon of defensive adaptation. Its very name, meaning shield reptile, is a testament to its most striking feature, a body encased in a mosaic of thick, bony plates known as scutes. These scutes, embedded deep within the skin, formed an interlocking barrier that protected the animal from head to tail, turning its entire body into a living shield. Scutosaurus was not built for speed. Reaching lengths of up to 2.5 meters and weighing nearly half a ton, it moved with deliberate, ponderous steps across the arid Permian plains. Its limbs, sturdy and robust, supported a frame designed to withstand the crushing jaws and slashing teeth of apex predators like Inostrancevia. When threatened, Scutosaurus could hunker down, presenting its armored flanks and making itself an unyielding obstacle. Yet Scutosaurus was not alone in this evolutionary experiment. The Archosaurs, a diverse group of herbivores, took defensive adaptation to new extremes. Among them, Bradysaurus was a true giant, surpassing Scutosaurus in both size and mass. At over 3.5 meters long and weighing more than a ton, Bradysaurus was a behemoth, its bulk alone deterring all but the most determined carnivores. Bradysaurus moved with a sprawling gait, its legs splayed outward, supporting its immense weight as it lumbered through the prehistoric undergrowth. Its size was its greatest defense, but its skull was equally remarkable, ornamented with an array of bony knobs, ridges, and bosses. These features may have served as visual signals to other Periosaurs, aiding in species recognition or intimidating rivals, and perhaps even played a role in ritualized combat. The Permian landscape was also home to moschops, one of the most successful herbivores of the Middle Permian. This barrel-chested animal, measuring about 2.5 meters in length and weighing close to a ton, was instantly recognizable by its massive, thickened skull. The bone of its forehead could reach up to 10 centimeters in thickness, forming a natural battering ram. For decades, paleontologists debated the function of Moschop's reinforced skull. The prevailing view now is that these animals engaged in head-butting contests, much like modern rams or goats. Such behavior would have been used to establish dominance within herds, secure territory, or compete for mates. These contests, played out in slow-motion clashes, reveal a level of social complexity rarely seen in such ancient animals. The daily lives of these herbivores revolved around the relentless search for food. The Permian world was dominated by tough, fibrous plants, and these animals were the primary consumers. Their massive bodies housed extensive digestive systems, capable of breaking down the most resistant vegetation. Day after day, herds of moschops, Scutosaurus and Periosaurs grazed across the landscape, shaping the very environment through their feeding. While predators like the Gorgonopsids evolved ever more lethal adaptations, razor-sharp teeth, powerful jaws, and increased speed, the herbivores responded with passive resistance. Some became too large to tackle, others too well armored to penetrate, and still others developed social strategies to deter attackers. The result was a dynamic ecosystem, a constant interplay of offense and defense. In this world, survival depended not just on the ability to hunt, but on the ability to endure. The Permian herbivores, with their fortress-like bodies and complex behaviors, were the last kings of a world on the brink of transformation, living monuments to the power of evolution in the face of extinction. The Permian period was a crucible of evolutionary innovation, where only the most adaptable could hope to endure. The world was harsh and unpredictable, vast stretches of arid land, searing heat by day and chilling cold by night. In this unforgiving environment, survival was not a matter of brute force alone, but of intricate, finely tuned strategies honed over millions of years. Among the most remarkable evolutionary leaps was the emergence of endothermy, warm-bloodedness, in the therapsids. Unlike their cold-blooded contemporaries, these proto-mammals developed the ability to internally regulate their body temperature, a trait that would eventually define the mammalian lineage. This adaptation allowed therapsids to remain active during the cooler twilight hours and even into the night, exploiting times when their reptilian competitors were sluggish and vulnerable. By expanding their window of activity, they could hunt, forage, and evade predators with greater flexibility. However, maintaining a constant internal temperature came at a steep metabolic cost. Therapsids required a steady influx of food to fuel their high-energy lifestyles, driving them to become persistent and opportunistic hunters and foragers. This relentless need for energy shaped their behavior and physiology. Therapsids evolved powerful limbs and efficient respiratory systems, enabling them to pursue prey over long distances and outlast their quarry through sheer stamina, a stark contrast to the short, explosive bursts typical of cold-blooded predators. While predators honed their offensive capabilities, herbivores responded with an array of defensive adaptations, each tailored to the unique threats of the Permian landscape. The massive Scutosaurus and its kin, the Periosaurs, became living fortresses. Their bodies were encased in thick, interlocking bony plates, forming a formidable barrier against even the most determined attackers. These osteoderms were not merely passive protection. Their very presence discouraged predators, signaling that any attack would be costly and potentially futile. A predator attempting to pierce this armor risked shattering its own teeth, suffering injury, or losing precious time and energy. An evolutionary arms race played out in bone and tooth. Other herbivores, such as moschops and Ankylosaurus, developed massive, reinforced skulls. These thickened crania served multiple functions, from defense to social interaction. In fierce contests for mates or territory, these animals would engage in head-butting duels, their skulls absorbing and distributing the force of impact. In the face of a predator, the same adaptations shielded their vulnerable brains, transforming their heads into both weapons and shields. Predators, in turn, evolved specialized tools and tactics to counter these formidable defenses, each adaptation a response to the challenges posed by their prey. The fearsome Inostrancevia, for example, wielded elongated, saber-like canine teeth. Rather than attempting to crush armor, it targeted the soft, vulnerable regions of its prey, such as the neck, delivering a single precision bite that could sever arteries and bring down even the most heavily armored herbivores through rapid blood loss. In contrast, Rubigia relied on sheer brute force. Its massive jaws, powered by robust musculature and reinforced bone, could generate enough pressure to crack open the armored defenses of its prey, allowing it to access the nutrient-rich flesh beneath. Not all predators relied on size or strength. The smaller Lycaenops adopted a different approach, using stealth and agility to its advantage. Its proportionally large eyes suggest a nocturnal lifestyle, allowing it to see in low light and ambush unsuspecting prey under the cover of darkness. By hunting at night, Lycaenops could avoid direct competition with larger diurnal predators and exploit a unique ecological niche. Beyond physical adaptations, social behavior emerged as a powerful survival tool. Many Permian herbivores formed herds, their collective vigilance and cooperation providing safety in numbers. Fossil evidence of healed injuries and wear patterns on skulls suggests that moschops engaged in ritualized combat within groups, establishing social hierarchies and strengthening bonds that would help the herd function as a cohesive unit. Living in groups offered multiple advantages: more eyes to detect danger, the ability to mob and drive off predators, and increased efficiency in locating scarce resources like food and water in the arid Permian landscape. Even among predators, cooperation could be a game-changer. Packs of Lycaenops may have coordinated their attacks, using teamwork to bring down prey much larger than themselves, an early example of the social hunting strategies that would later define mammalian carnivores. In the end, it was this remarkable diversity of adaptations, ranging from internal thermoregulation and specialized weaponry to complex social structures, that enabled the animals of the Permian to thrive in a world of constant challenge and change. Each strategy, whether offensive or defensive, solitary or social, was a testament to the relentless drive for survival in one of Earth's most demanding eras. The reign of the Permian monsters, which had dominated the planet for millions of years, ended not with a single cataclysm but with a relentless, all-encompassing disaster that swept across every corner of the ancient world. Approximately 252 million years ago, Earth was plunged into the most devastating extinction event in its entire history, a calamity so overwhelming that it is remembered as the Great Dying. This was not merely a loss of species, but a near-total collapse of the planet's biosphere. The extinction unfolded as a prolonged sequence of environmental catastrophes. Over thousands of years, the planet was battered by a relentless barrage of disasters, each compounding the effects of the last, and each pushing life closer to the edge of oblivion. The initial spark for this global crisis was the eruption of the Siberian Traps, a vast region of volcanic activity in what is now northern Russia. These eruptions were unlike anything the planet had ever seen, covering millions of square kilometers with rivers of molten rock. For hundreds of thousands of years, the Siberian Traps belched forth lava and ash, releasing energy and material on a scale that dwarfs even the largest modern eruptions. The landscape was transformed into a hellish expanse of fire and stone. With each eruption, vast quantities of greenhouse gases, primarily carbon dioxide and methane, were injected into the atmosphere. These gases trapped heat, disrupting the planet's climate and setting off a chain reaction of environmental changes. The result was a dramatic and sustained rise in global temperatures. The world's climate spiraled out of control, with heat waves scorching the land and turning once lush regions into arid wastelands. As the atmosphere warmed, the oceans absorbed much of this excess heat. The water became stratified, preventing the mixing of oxygen-rich surface layers with deeper waters. Vast stretches of the ocean floor became anoxic, devoid of oxygen, creating immense dead zones where only the hardiest microbes could persist. The volcanic eruptions also released enormous amounts of sulfur dioxide, which combined with atmospheric moisture to produce acid rain. This toxic precipitation fell relentlessly, leaching nutrients from the soil, poisoning waterways and devastating plant life across entire continents. As forests withered and plant life perished, the intricate web of life that depended on them began to unravel. Herbivores starved as their food sources vanished, and the predators that relied on them soon followed. The devastation was absolute. Across the continents, the bodies of once mighty creatures lay scattered in barren wastelands, victims of starvation, toxic air, and a collapsing ecosystem. In the oceans, the crisis was even more severe. Up to 96% of all marine species, corals, brachiopods, ammonoids, and countless others, were wiped out, leaving the seas eerily empty and silent. Iconic groups like the trilobites, which had survived multiple previous extinctions and flourished for over 250 million years, vanished completely, their long evolutionary journey ending in silence. On land, the destruction was nearly as complete. 70% of all terrestrial vertebrate species disappeared, including many dominant reptilian and amphibian lineages that had once thrived in the Permian world. Apex predators, such as Inostrancevia and Rubigia, once rulers of their ecosystems, found themselves in a barren world. With their prey gone, these formidable hunters succumbed to starvation, their reign brought to a slow and desperate end. Even the heavily armored herbivores like Scutosaurus, adapted to withstand the attacks of predators, were defenseless against the collapse of their environment. With toxic air and vanishing vegetation, they too faded from existence. The Great Dying was a silent, inexorable force. There was no single moment of destruction, only the gradual, suffocating loss of life as the planet's systems failed. Unlike the sudden violence of an asteroid impact, this extinction left no crater, no single scar upon the land. Instead, it was marked by a slow, relentless transformation, a world growing ever more inhospitable day by day. Over time, the vibrant ecosystems of the Permian faded away, replaced by barren expanses and lifeless plains. The transformation was so gradual that it would have been almost imperceptible to any surviving witness, yet its effects were total. The sky, once blue and clear, became a permanent, suffocating haze of volcanic dust. The air was thick with ash and toxic gases, making every breath a struggle for survival. For millions of years, Earth remained a desolate wasteland, a shadow of its former self, stripped of its diversity and vitality. Only a handful of resilient species managed to cling to existence, eking out a precarious survival in the ruins of a once thriving world. Life teetered on the brink, closer to total extinction than at any other time in the planet's history. The world of the Permian Kings was erased, leaving behind a profound silence, a haunting reminder of the fragility of life and the immense power of Earth's natural forces. In the aftermath of the Great Dying, the Earth was transformed into a realm almost unrecognizable from the vibrant world that had come before. The Permian's lush forests and teeming rivers had vanished, replaced by a stark, silent expanse of devastation. The early Triassic, spanning millions of years after the extinction, was marked by a haunting emptiness. Once thriving plains now stretched endlessly, barren and lifeless, with only the faintest hints of green clinging to the parched soil. The intricate web of life that had defined the Permian period was gone. Forests that once towered overhead were reduced to scattered remnants, their trunks blackened and broken, their canopies lost to time. In place of ancient trees, only the hardiest plants survived. Ferns and lycophytes, low to the ground and quick to colonize the open spaces. These pioneers formed thin carpets of green, struggling to reclaim the land from the grip of desolation. The world was subdued, its silence broken only by the whisper of wind across empty plains. The mighty Gorgonopsids, with their saber-like teeth, and the lumbering Archosaurs, once rulers of the land, had vanished. No longer did their calls or movements disturb the stillness. The plains were devoid of large animals, their absence a stark reminder of the catastrophe. The climate itself had become a formidable adversary. Temperatures soared under a relentless sun, and the land was parched by drought. The atmosphere, thinned and oxygen-poor, made survival a daily struggle for any creature that remained. Only a handful of species endured these trials. Survival was not a matter of strength or size, but of adaptability. The creatures that persisted were those able to cope with scarcity, heat, and the ever-present threat of extinction. These survivors were typically small, resilient animals, creatures that could subsist on little food, burrow to escape the heat, and tolerate the low oxygen levels that suffocated larger forms. Their bodies and behaviors were shaped by necessity, each adaptation a testament to their tenacity. Among these remarkable survivors was Inostrancevia, a squat, beaked herbivore whose lineage had weathered the storm. Inostrancevia, about the size of a modern pig, was unassuming in appearance. Its sturdy body and powerful jaws allowed it to dig for roots and tubers, extracting nourishment from the toughest plants left in the wasteland. For a brief window in Earth's history, Inostrancevia became the planet's most successful land vertebrate. In some fossil beds, their remains make up as much as 95% of all vertebrate fossils, a testament to their dominance in a world emptied of rivals. Inostrancevia was what paleontologists call a disaster taxon, a species that flourishes in the wake of ecological collapse, not because it outcompetes others, but because so few competitors remain. Yet the world it inherited was harsh and colorless, a landscape stripped of diversity and complexity. Inostrancevia wandered alone or in small groups, their lives a daily struggle for survival. The food webs of the early Triassic were astonishingly simple. Inostrancevia and a handful of other herbivores grazed on the sparse vegetation, while small, opportunistic predators, unspecialized and few in number, hunted them. Gone were the intricate layers of the Permian food chain. Apex predators, mid-level carnivores, and a diversity of herbivores had all been swept away, leaving behind a flattened ecosystem with little variety. The recovery of life was agonizingly slow. Over millions of years, plants began to reclaim the land, their roots stabilizing the soil and their leaves capturing sunlight, laying the groundwork for future ecosystems. The earth itself was healing, but at a pace measured in geological time. Erosion sculpted new landscapes, and the slow return of vegetation signaled the first steps toward recovery. The climate remained volatile, with wild swings between scorching heat and chilling cold. The atmosphere's low oxygen content stunted animal growth and limited activity, further slowing the resurgence of life. Each sunrise over the empty plains marked another day in a long, silent era, a time of waiting as the planet's biosphere slowly rebuilt itself from the brink. The extinction of the dominant Permian animals left behind a vast ecological vacuum. The niches once filled by powerful predators and diverse herbivores now stood empty, open to any life form capable of adapting to the new world. The land was a blank canvas, its surface scarred but ready for new beginnings. Every patch of open ground, every unclaimed resource represented an opportunity for evolution to take a new direction. The few survivors, though small and unremarkable, carried within them the genetic seeds of future diversity. Their ability to persist through adversity would shape the next chapter in the history of life. As the sun rose over the barren land, subtle signs of renewal began to appear, tiny shoots of green, the scurrying of small animals, the first hints of a new era. In the shadows, a new lineage of reptiles, Archosaurs, began to emerge. Once minor players in the Permian world, they now found themselves poised to inherit the Earth, ready to seize the opportunities left by the extinction and begin a new evolutionary dynasty. In the aftermath of the Great Dying, the world was transformed into a desolate expanse. Over 90% of marine species and 70% of terrestrial vertebrates had vanished, leaving behind a barren, silent landscape. Yet, amid the devastation, life persisted. From the shadows of extinction, a new lineage of reptiles began to emerge, creatures that would come to dominate the next era. These were the Archosaurs, a group whose name means ruling reptiles. They were not the largest or most numerous survivors at first, but they possessed a suite of evolutionary advantages that would soon tip the balance of power in their favor. During the late Permian, Archosaurs had existed only on the fringes, overshadowed by the dominant therapsids, mammal-like reptiles that ruled the land with their size and strength. The Archosaurs, in contrast, were small, agile, and largely inconspicuous, eking out a living in the margins of a world not yet their own. But the Triassic world was a harsh, unforgiving place. Temperatures soared, rainfall was scarce, and vast deserts stretched across the continents. The Archosaurs, however, were uniquely equipped for survival in these extreme conditions. Their bodies were designed for efficiency. With upright limbs positioned beneath their bodies, Archosaurs could move swiftly and breathe more effectively than their sprawling synapsid competitors. Specialized skin reduced water loss, and their advanced respiratory systems allowed them to thrive where others faltered. As the climate gradually stabilized, the barren landscapes began to recover. Hardy plants took root, and food webs slowly reassembled. The Archosaurs, with their resilience and adaptability, expanded into the newly available ecological niches, quickly becoming a dominant force in the recovering world. This lineage diversified at an astonishing rate. Some Archosaurs evolved into swift predators, others into robust herbivores, and still others into specialized scavengers. Each new form filled a gap left by the vanished Permian giants, reshaping the fabric of life on land. One remarkable branch of the Archosaur family tree adapted to aquatic environments. These were the ancestors of modern crocodiles, powerful, stealthy predators that soon dominated the rivers, lakes, and swamps, preying on anything that ventured too close to the water's edge. Another lineage took to the skies. The pterosaurs, with their elongated fingers supporting vast membranous wings, became the first vertebrates to master powered flight. They soared above the Triassic landscapes, hunting for fish and insects, and opening up a new aerial frontier. Yet the most transformative branch of all remained earthbound. These were the earliest dinosaurs, small bipedal hunters and foragers, perfectly adapted for speed and agility in the dense Triassic forests. Over time, these pioneering dinosaurs diversified rapidly. They grew larger, more specialized, and more numerous, steadily outcompeting the remaining synapsids for food and territory. Their superior locomotion and efficient breathing gave them a crucial advantage in the race for survival. The rise of the dinosaurs was not a sudden event. For millions of years they coexisted with a diverse array of other Archosaurs and the last of the synapsids, who themselves were evolving into the earliest mammals, small nocturnal creatures eking out an existence in the shadows. This was a time of experimentation and transition. The world was a patchwork of old and new, with ancient lineages fading as innovative newcomers rose to prominence. The first true mammals, descendants of the synapsids, began to carve out their own ecological roles, setting the stage for future evolutionary dramas. As the Triassic period advanced, the dinosaurs' anatomical innovations, such as their upright stance, efficient lungs, and active metabolism, allowed them to exploit resources more effectively than any other group. Their dominance became increasingly apparent as they spread across the continents. At the close of the Triassic, another extinction event struck, triggered by massive volcanic eruptions and climate upheaval. This catastrophe eliminated many of the dinosaurs' remaining rivals, clearing the way for their unchallenged ascendancy. With the dawn of the Jurassic, the age of dinosaurs began in earnest. For over 150 million years, these extraordinary animals would dominate every terrestrial ecosystem, evolving into an astonishing diversity of forms, from towering sauropods to armored stegosaurs and swift, cunning predators. Yet the story of the Permian monsters remains a vital chapter in Earth's history. These formidable creatures, with their bizarre adaptations and fierce competition, shaped the evolutionary landscape that made the rise of the Archosaurs possible. The Permian world was a crucible of extremes where only the most resilient survived. But even the mightiest fell before the onslaught of global catastrophe, their reign ended by forces beyond their control. In their absence, the stage was set for new dynasties. The extinction of the Permian giants, as tragic as it was, opened the door for the Archosaurs, and ultimately the dinosaurs, to inherit the Earth. The legacy of the Permian is a testament to both the fragility and resilience of life. Extinction, though devastating, is also a force of renewal, resetting the evolutionary clock and allowing new forms to rise from the ashes of the old. The last kings of the Permian vanished into prehistory, their bones entombed in stone. Yet their downfall was not the end, but the beginning of a new chapter, one that would see the rise of the most iconic creatures ever to walk the earth. Beneath the towering shadows of the Permian's mighty beasts, another world thrived, one far less imposing, yet equally influential in shaping Earth's deep history. This was the world of the Permian forests, vast and varied ecosystems that served as the true engines of evolution during this tumultuous era. Stretching across the supercontinent Pangaea, Permian forests were unlike any the world would see again. In the humid lowlands, dense stands of ancient seed ferns, Glossopteris, formed sprawling woodlands that blanketed river valleys and floodplains. Their broad, tongue-shaped leaves captured sunlight and fed immense root systems, stabilizing soils and fueling cycles of growth and decay. High above, primitive conifers and towering cordates reached skyward, their woody trunks and needle-like foliage adapting them to drier uplands where water was scarce. These forests were not merely backdrops, they were dynamic, living systems. Their fallen leaves and branches created thick mats of litter teeming with decomposers, fungi, bacteria, and the earliest soil-dwelling arthropods. In this churning detritus, nutrients cycled endlessly, supporting a hidden web of life from the tiniest springtails to burrowing amphibians. The Permian forests also played a crucial role in the planet's climate. Through photosynthesis, they absorbed vast quantities of carbon dioxide, influencing atmospheric composition and helping to regulate global temperatures. But as the Permian progressed, tectonic upheaval and shifting climates led to dramatic changes. The lush coal swamps of the Carboniferous faded, replaced by more drought-tolerant flora. Massive volcanic eruptions spewed ash and gases into the sky, darkening sunlight and acidifying rain. In response, the forests adapted or perished. Amid these upheavals, the evolution of seeds marked a silent revolution. Unlike their spore-bearing ancestors, seed plants could survive longer droughts and colonize new, harsher environments. Their tough outer coats protected embryos, allowing them to wait for the perfect moment to sprout. This evolutionary leap gave rise to new plant lineages and enabled the spread of forests into previously inhospitable regions. Within these forests, evolutionary arms races unfolded. Herbivorous synapsids and early reptiles developed specialized teeth and digestive systems to exploit the tough, fibrous vegetation. In turn, many plants evolved defensive strategies: thick bark, toxic chemicals, and spiny leaves, setting the stage for a co-evolutionary dance that would echo through the ages. Yet, as the Permian drew to a close, these forests faced their greatest challenge. Rapid climate shifts, combined with the devastation of the Great Dying, led to the collapse of many woodland ecosystems. The loss of plant diversity reverberated through food webs, triggering cascading extinctions among the animals that depended on them. Still, the legacy of the Permian forests endures. Their fossilized remains, coal seams, petrified wood, and leaf imprints are silent witnesses to a world transformed. The innovations born in these shadowy groves, seeds, wood, and complex root systems, would shape the future of life on land, providing the foundation for the forests and jungles that followed. In the story of the Permian, the forests were not merely scenery, they were catalysts of change, silent architects of evolution, and the green engines that powered the rise and fall of ancient worlds. Above the tangled canopy of the Permian forests, another realm unfolded, one seldom glimpsed, yet vital to the fabric of this ancient world. The Permian skies were more than empty expanses. They were dynamic corridors of weather, migration, and chemical transformation, profoundly shaping the course of life below. During the Permian, Earth's atmosphere was in flux. Oxygen levels, once soaring during the Carboniferous, began a slow but inexorable decline. This subtle shift rippled through ecosystems, influencing the size and diversity of aerial and terrestrial life alike. The giant insects of earlier ages, dependent on abundant oxygen to fuel their flight, gradually dwindled in both number and stature, making way for smaller, more adaptable species. The winds themselves were agents of change. Sprawling across the supercontinent Pangaea, the land masses' sheer size disrupted global air currents. Seasonal monsoons swept across interior deserts, while coastal regions endured wild swings between drought and deluge. Volcanic eruptions, frequent and ferocious, spewed ash and sulfur high into the atmosphere, dimming sunlight and triggering acid rains. These atmospheric disturbances could last for years, plunging regions into sudden cold snaps or prolonged darkness, with devastating consequences for life on the ground. Yet the skies were also highways for life. Early flying insects, including the ancestors of modern dragonflies and beetles, darted through sunbeams in search of mates and prey. Their delicate wings mirrored the shifting patterns of plant evolution below, with some species evolving tougher exoskeletons and specialized mouthparts to exploit the changing floral landscape. Pollen and spores carried on the wind, traveled vast distances, crossing mountains, rivers, and even continents. This aerial dispersal enabled plants to colonize new habitats, fueling the spread of drought-resistant conifers and the rise of seed-bearing flora. Each gust of wind was a thread in the tapestry of evolution, weaving together distant populations and driving genetic diversity. Clouds, too, played their part. They regulated temperature, delivered life-giving rains, and shielded the land from the harsh glare of the sun. Their shifting shadows marked the passage of seasons, signaling migrations and triggering the cycles of growth and dormancy that defined Permian life. As the Permian period waned, the skies grew increasingly volatile. Massive volcanic provinces darkened the horizon and the atmosphere became laced with greenhouse gases. These changes tipped the planet into chaos, amplifying global warming and acidification, factors that would ultimately contribute to the greatest mass extinction in Earth's history. The Permian skies, ever restless, were both cradle and crucible. They shaped the destiny of forests and rivers, mountains and deserts, the mighty and the minute. In their vast, unseen currents, the story of life's resilience and its vulnerability was written across the face of an ancient world. Beneath the towering forests and shifting skies of the Permian, another world thrived in the shadows, one of decay, transformation, and silent industry. Here in the cool, damp understory, and within the rich, dark soil, fungi and decomposers played a vital role as the planet's unseen architects. The Permian landscape, dominated by conifers, seed ferns, and horsetails, produced vast amounts of organic matter. Fallen leaves, dead wood, and animal remains accumulated in thick layers, forming the raw material for the next stage in the cycle of life. It was the fungi, primitive yet remarkably efficient, that broke this material down, unlocking nutrients and returning them to the ecosystem. Early fungal species, including ancient relatives of today's mushrooms and molds, colonized decaying plant matter with intricate networks of thread-like hyphae. These hyphae secreted powerful enzymes capable of digesting tough compounds like lignin and cellulose, substances that even most bacteria could not break down. In doing so, fungi accelerated the decomposition of woody debris, clearing the forest floor and nourishing new growth. This process was fundamental to Permian ecosystems. Without efficient decomposers, dead plant material would have choked the land, trapping carbon and stalling the cycle of nutrients. Instead, fungi acted as nature's recyclers, ensuring that minerals and elements flowed continuously from one generation to the next. The work of fungi also shaped the chemistry of the soil and atmosphere. By breaking down organic matter, they released carbon dioxide and other gases, subtly influencing the planet's climate. Their activity helped to regulate soil acidity, support complex microbial communities, and create fertile ground for plants to take root. Not all fungi were confined to the forest floor. Some formed symbiotic relationships with living plants, wrapping around roots in elaborate partnerships known as mycorrhizae. These connections allowed plants to absorb water and nutrients more efficiently, boosting their resilience against drought and disease, a critical advantage in the unpredictable Permian world. Other decomposers, such as ancient millipedes, beetles, and nematodes, joined the fungi in this subterranean ballet. Together they formed a vast, interconnected web of life, invisible yet indispensable. Through their tireless labor, the silent architects of the Permian shaped the destiny of entire ecosystems. They forged the foundation upon which forests grew, rivers flowed, and animals thrived. In the quiet darkness beneath ancient trees, the pulse of life beat on, sustained by the ceaseless work of organisms too small to see, but too important to forget. As the Permian era unfolded, not all life was confined to the vast landscapes, towering forests, or the underbrush teeming with decomposers. Beneath the shimmering surfaces of ancient seas, a world equally rich and complex thrived, playing host to an array of organisms that would shape the course of evolution. The Permian seas were a dynamic and ever-changing environment, teeming with life forms that ranged from the simplest plankton to the most formidable marine predators. These waters were home to a diverse array of marine invertebrates, including brachiopods, ammonoids, and crinoids, whose fossilized remains offer us a window into this bygone world. These creatures were not merely passive inhabitants. They were active participants in a delicate and intricate web of life. Brachiopods, resembling clams but belonging to a different lineage, anchored themselves to the seabed with muscular stalks, filtering plankton from the water with their feathery feeding arms. Ammonoids, with their spiral shells and jet propulsion capabilities, were agile predators, hunting smaller marine organisms with precision and speed. Crinoids, often referred to as sea lilies, extended their feathery arms into the currents, capturing microscopic food particles drifting by. Among these invertebrates swam the early ancestors of modern fish. Primitive sharks patrolled the waters, their streamlined bodies and keen senses making them adept hunters. Bony fish, with their varied shapes and sizes, explored every nook and cranny of the marine environment, from shallow coastal waters to the deeper oceanic realms. The Permian seas were not just a stage for individual species, they were cradles of evolutionary innovation. Reef-building organisms, such as sponges and corals, constructed massive underwater structures that provided habitats for countless other species. These reefs were bustling cities of the marine world, where symbiotic relationships flourished and competition drove the evolution of new adaptations. The chemistry of the Permian seas was also in flux. Shifts in oceanic circulation patterns, volcanic activity, and changes in atmospheric conditions influenced the levels of oxygen and carbon dioxide in the water. These fluctuations could create both opportunities and challenges for marine life, driving evolutionary pressures that shaped the resilience and adaptability of species. As the Permian period drew to a close, the seas bore witness to dramatic changes. Catastrophic events such as massive volcanic eruptions and the resultant climate shifts triggered the most severe mass extinction in Earth's history. The Permian Triassic extinction event wiped out nearly 90% of marine species, leaving behind a stark and barren seascape. Yet, from this devastation emerged the seeds of new life. The survivors of the Permian seas laid the groundwork for the explosive diversification of marine life in the Triassic period. The lessons learned in the crucible of the Permian seas, adaptation, resilience, and innovation, would echo through the ages, shaping the future of life on Earth. In the depths of those ancient waters, the legacy of the Permian seas endures, a testament to the relentless and ever-changing nature of evolution. It is a reminder that even in the face of overwhelming odds, life finds a way to endure, adapt, and flourish. As the Permian period advanced, vast stretches of Earth's surface transformed into arid, inhospitable deserts, landscapes forged by relentless fire and ceaseless wind. The shifting supercontinent of Pangaea, with its immense interior far from the moderating influence of the oceans, birthed some of the most extreme and expansive deserts in the planet's history. Here the sun scorched the ground by day, while frigid darkness claimed the night, creating an environment of dramatic contrasts and formidable challenges. In these barren expanses, the land was dominated not by lush forests or teeming wetlands, but by sweeping dune fields, salt flats, and rocky outcrops. Red-hued sandstones and siltstones laid down by ancient rivers and wind-blown sediments painted the landscape in ochres and rusts, colors that endure in the fossil record to this day. Occasional seasonal rains carved ephemeral riverbeds, but for much of the year, drought reigned supreme. Despite these harsh conditions, life found ways to persist. Hardy plants such as seed ferns and early conifers adapted to survive with minimal water, developing deep roots and waxy coatings to conserve precious moisture. These pioneers stabilized the shifting sands, providing rare islands of shade and sustenance in the relentless sun. Animal life, too, evolved remarkable strategies to endure. Reptiles with thick, scaly skin minimized water loss, while some burrowed deep into the earth to escape the heat. Insect life flourished underground or emerged during the brief cooler twilights. Even the early mammal-like therapsids, ancestors of future mammals, adapted to the unforgiving terrain, seeking shelter in rocky crevices and relying on keen senses to locate scarce food and water. The Permian deserts were not lifeless wastelands, but crucibles of adaptation and innovation. The selective pressures of heat, dryness, and scarcity drove the evolution of resilience, shaping lineages that would one day radiate into new environments. These deserts also served as natural barriers, isolating populations and fostering the emergence of unique species found nowhere else on Earth. As the Permian drew to its cataclysmic close, the story of these deserts was etched into stone, preserved in the fossilized remains of plants and animals that braved the extremes. Their legacy is a testament to life's tenacity, a reminder that, even in the harshest environments, evolution never stands still, and the seeds of future worlds are sown in the silence of the sand.